Okay. So now I'm going to give some introduction to quantum computing. So before I get into the algorithms part, which is going to use a lot of qubits and unitaries and stuff like that, I will explain what a qubit looks like and how we can evolve it and how we can extract computation using these qubits, okay? So let me begin. Yeah, okay. So now we have like a lot of quantum computing research that is happening all over the world. Many of them even have their own quantum computers now, small ones, but still. But the enormous amount of research that is going into this is, in some sense, scary for cryptographers. But why quantum computing even began? So in some sense, it was because when these chips were becoming smaller and smaller, people started also looking at quantum effects that was not desirable for classical world. But then people thought, okay, why not use these quantum effects towards computation, especially when they are hindering? So that also kind of probed the question of what can we do with a quantum computer or with quantum particles interacting. And a more promising reason is also because people saw theoretical speed-ups in computational tasks, which 2 or 3 of them I will be discussing in this talk today. We will at least get the theoretical idea behind it. And also, it is interesting to know what nature has to offer us and how we can exploit nature towards our computation, right? It's like we as humans, we are always curious and we want to exploit nature for our computation. So yeah, these are the primary reasons why quantum computing is being researched. But before I get into quantum computing, I will have to describe what a qubit is, okay? So let's start. So if I have a single bit of memory, how many configurations can this single bit be in? 2, right? It's 0 and 1, okay? What about 2 bits of memory? How many configurations? 4, right? It's 0, 0, 0, 1, 1, 0, and 1, 1. What about 3 bits? 8, okay. And what about k bits? 2 power k, right? So we have like, if I have a k-bit register, classically, like classical k-bit register, then I can store any of these 2 power little k values in my register, but not all of them, right? Okay. But what if I said, quantumly, you can store all of them at the same time? Meaning, so if I have a k-bit quantum register, not only can I store just one of these 2 to the power k values, but I can store all of these 2 power k values at the same time in my k-bit register. Well, there's drama happening here. Yes, we can store, but what we can do with them is still a question. And qubits allow us to do that. So what qubits let me do is I can create a superposition of all these possible states that my memory can be. And this is what we will exploit soon. Okay? So classically, before I get into k-qubit systems, I will first describe how a 1-qubit system looks like. Then we will slowly build onto how a general n-qubit system looks like, okay? So again, to draw the contrast, classically, I can have my memory register of 1 bit as 0 or 1, but quantumly, I can have it as a vector, meaning like I can store all my possible memory states in that single qubit. And the best part is I can store it with some amplitudes. So this alpha and beta here are representing an amplitude. They do have to satisfy some conditions. I will get there. And another interesting part is what nature allows us to do is to have these alpha betas as complex numbers. So they're not just positive numbers or real numbers, they're complex numbers. So you can even have negative values associated with alpha and beta, which will help us to have interference, which we will see in some slides later. Now, what are the conditions that are required for this alpha and beta? That they both should sum up to, their amplitude square should sum up to 1, okay? We'll see what is happening. But you kind of get it, like, so in some sense, with alpha mass, my quantum register is in state 0, and with some sense, with beta mass, my quantum register is in state 1. This is what is happening. And I can express my quantum state, like a single qubit state, as a vector of 2 dimension. So I have like alpha times possibility of state 0 and beta times possibility of state 1. Is this kind of clear? Okay. Now what will help you is if you, instead of thinking of qubit as some strange particle, which I mean it is strange, but instead of thinking of it as a strange physics thingy that we cannot grasp, just think of these qubits as just elements in vector space. Like it's just a single qubit is nothing but a 2-dimensional vector with complex values alpha and beta. Okay? And we will see how we can evolve these alpha betas to towards desirable computation. Cool. And this is, and notationally, the 0 state is written as this, it's called ket 0, and this is written as, this is called ket 1. So this strange triangular brackets are just the notation called ket. Okay. So now quick question, how many single qubit quantum states are possible? Sorry? So I'm saying any state that satisfies these conditions, these are complex values that satisfy this condition, is a quantum state. Yes, infinitely many, right? Because I can have arbitrary precision, like I can just have any, forget about complex numbers, I can even have just with real numbers the whole infinity line, right? Yeah? Okay. Now let's get further. Yeah. So now I said, okay, I kind of described what a qubit looks like, right? But how do we do computation on a qubit? How do we do computations on a classical computer usually? So we have these bits, right? Then in some sense we apply gates, right? AND gates or NOT gates or XOR gates or whatever, these tiny gates that we apply. Then whatever value is stored in these bits get manipulated to whatever it should become after the application of the gates. Similarly, in the quantum world, we also apply gates, but these, because it's a thing in the nature, it can only, like any quantum state can only get unitarily transformed to another quantum state. These are some restrictions that quantum mechanics enforces, but we'll see. So I can basically do a unitary evolution that takes any quantum state, say this was a quantum state, right, because it satisfied this condition, to another quantum state, which is some different value gamma and delta, but must also satisfy this condition. And this gamma and delta also should be complex numbers. And this transformation has to be a unitary transformation. This is like I said, if you kind of consider these two as just this as a 2-dimensional matrix, which is containing alpha and beta, your final answer should be again a 2-dimensional matrix, vector, which is gamma and delta. And this unitary evolution, suppose I denote it by U, should be an evolution that satisfies U times U dagger equals to identity. Okay, that's just a mathematical definition of unitary evolution. And quantum mechanics tells us that our evolution happens via these kind of mathematical operations. Okay? Yeah? Cool? Okay. Now, let's look at some examples of these unitary evolutions. Okay? Like I said, I can write basically, so I said I can express a unitary evolution as any matrix, a 2x2 matrix, which would satisfy U times U dagger equals to identity, right? But now, any unitary matrix, I can also write it with the basis, and these will be just the I, Z, X, and IY will be just the basis of the matrix, and you can just write any unitary operation as a linear combination of these matrices. But let's look at some matrices so that you can get an idea of what a gate looks like, okay? Yeah. Okay. Now, okay, let's see. So this is, say, identity. Now, identity matrix on any vector will just keep the vector as it is, okay? So nothing, identity doesn't do much. I mean, doesn't do anything. Then we have this Z gate. Now look at this Z gate. What it does is, it doesn't change if the quantum state is in 0 state, that is ket 0, it doesn't change anything, it just makes it exactly same. But if it is applied on the 1 state, it kind of flips, it adds a phase, okay? So Z gate on a ket 1 state will actually become -1, minus ket 1, okay? Now H gate, Hadamard adds like a superposition. So if I apply Hadamard on the 0 state, I get basically my alpha and beta to be equal to 1 by square root 2. And if I apply Hadamard to 1 state, I get the same state but with a minus sign here. We will soon see some more examples that will make it more clear. And X gate, this is kind of like NOT gate in the classical setting. When you apply the X gate on ket 0, that becomes ket 1. If you remember, this is ket 1, see here. And if I apply the X gate to 1 state, then it becomes 0. So in some sense, what X gate is working like is a NOT gate. It takes a 0 state, brings it to 1 state, and vice versa, okay? Now let's look at this computation on a general single qubit state and not like a single qubit state with no amplitude, like with no interesting alpha beta value, just to see what the states become, okay? Like I said, these are just unitary evolution, right? And these quantum states are just vectors. So any application, you can kind of do it linearly. So you can apply this. So if this is my state, this is basically just alpha times this much plus beta times this much. If I apply identity, anyway, identity is an easy one, so you don't have to do anything. Now, if I want to apply Z, so what happens, I can do it linearly, right? So my Z on the first part doesn't do anything, so I will just get alpha times the same thing. Z on the second part will add a -1, so I end up getting alpha and minus beta. Yeah, you see, the Z is acting like adding a phase. Then H, again you do the same thing linearly. H on this will add 1 and 1 with square root 2, so this kind of becomes this. And also from beta you get that, so you get alpha plus beta. And similarly for -1, with 1 you'll get this quantity. This is easy to check, so don't worry. And X on this state psi is just flipping these values. See, if my state psi was alpha and beta, what my X does is changes this to 0, 1. So that's why alpha comes down, and changes this to 1, 0. That's why beta comes up. So it's basically flipping the amplitudes, the X gate. Okay? Any questions till now? No questions? Okay. We will get to the computation part soon. But before I do that, I have to kind of describe these objects. Okay. Yeah. So now I said how we can, like first I described what a qubit looks like. Then I told you how we can evolve a qubit, okay? But how do we extract information from it? So what we can do with a qubit is we can measure it, okay? And what happens is, suppose I have this qubit, which is with alpha mass 0 and beta mass 0, and it satisfies this condition. Then what I get is, after a measurement, is I get 0 with probability mod alpha square, and I get 1 with probability mod beta square. So if my alpha was 0 to begin with, if I measured, then I will only get ket 1. And if I had the state where beta was 0 to begin with, if I measured, then I would only get ket 0, this state. But if I had any superposition, this is called a superposition of states, then I would get this probability distribution. Now you see why this condition is enforced, because you want to make sure that these represent the probability. So this is the condition that it enforces. Cool? Yeah.
These measurement outcomes, they depend on the measurement choice.
Yeah. So I'm only talking about computational basis measurement, but you could change it to some other basis measurement as well. But that is equivalent to doing some unitary and then doing a computation basis. So is that what your question is? Okay. Okay. And another important thing, once you measure, once the outcome is, once you get an outcome, the state collapses to that of the measurement. So if I measured and I got this, yes, I get it with probability mod alpha square, but once I get it, my new state becomes this ket 0. And if I had got this, then my new state becomes get 1. This is what nature offers. I don't make the rules. Okay? So now let's quickly just go through what happens if I make a measurement after the application of these unitaries. Okay? I want to make a point here. So that's why I'm going to discuss what happens after we make a unitary and then we measure. So if I did I, my psi has not changed, right? So the measurement outcome still would be, with mod alpha square it will be 0, with mod beta square it will be 1. But if I do z, what will happen? The state has changed, but does the measurement outcome probabilities change? No, right? Because yes, I have a minus beta here, but the probability is still mod of this beta square, right? So this negative sign doesn't impact. But with Hadamard, the values change here, right? So the measurement probabilities are going to change. And with X, they flip. So now after application of X gate on my psi state, initially my psi state said, oh, the probability of measuring 0 was alpha square, but now it will be beta square because the mass has shifted. You see? So what we kind of notice is unitary evolution can in fact evolve the state, and when we measure, we will get a different outcome. Okay? And now when we want to exploit this thing, we will try to come up with these unitaries that actually help us to get a nice amplitude there. Okay? We'll see that. Any questions till now? No? Okay. Yeah. Okay. So like I said, single qubit system, you can write it as a 2-dimensional vector in complex space. And with a 2-qubit system, you just have now a bigger space, right? Because like I said, the number of possible memory configurations of a 2-qubit system, 2-bit system itself is 4. So my 2-qubit system is now going to be a 4-dimensional vector. So instead of alpha and beta, I will have 4 complex values associated with a 2-qubit system. And when I'm looking at a k-qubit system, I will have 2 to the k many these alphas that will be describing the system. Okay? Yeah, and this also has to satisfy this condition. Okay, but how do we write those states? Okay. Yeah. So remember, like for single qubit system, I kind of wrote it as 1, 0, and the ket 1 I wrote it as 0, 1. For a 2-qubit system, the 0, 0 state is nothing but 0 times 0, which is basically just basically I'm constructing the basis for a 2-dimensional 2-qubit system. Okay? So my 0, 0 is nothing but 1, 0, 0, 0 here. 0, 1 is 1 in the second position. 1, 0 will be 1 in the third position. Maybe I have it in the slide. Yeah. And 1, 1 will be the one in the last position. Now, if you notice, these do form a basis for my 4-dimensional system, and that is the basis for my quantum state as well. And just like we could evolve single qubit systems by using single qubit unitaries, we can also evolve 2 qubits. Oh, maybe I have to first describe this. Okay, sorry. Yeah, okay. Now, before I go into evolution, I want to kind of tell you one more thing, that is the entanglement. The sci-fi movies tell us about entanglement and teleportation and all that. While the movies don't really depict the correct thing behind it, but both entanglement and teleportation are really things that occur in nature. And mathematically, what entanglement means is, if I have, say, 2 states, psi, which is described as alpha and beta, and say phi, which is described by gamma and delta, the tensor product, these are just vectors, right? I can just tensor multiply them, will give me this state. Okay? So this is nothing but, see, I just opened up these vectors. I took alpha times gamma, alpha times delta, then beta times gamma, and beta times delta. These are my coefficients that I get. Now, if there is a state that I cannot write, so any state that I can write it as product, this tensor product of 2 states is a product state. But if there is a state that I cannot write it as a product state, then that is called an entangled state. Okay? And soon we will see why this is an entangled state. And we can construct these entangled state in labs. And also these have been useful in many computational tasks. We'll see. Now, okay, let's see the reason why this is an entangled state. Look, now how do we prove that this is an entangled state? So we prove it by contradiction. We say, let's say this state was not an entangled state. Then it must be a product state. And if it must be a product state, then it must have some representation in this way, right? Where I write it as alpha, gamma, and so on. But if I have this representation, if you guys notice, there are two terms that should have 0 coefficient, right? And two terms that should have 1 by root 2 as coefficient. So the two terms that have 0 coefficients are these. So my alpha and delta should be 0, my beta and gamma should be 0. That means their product should be 0. But from these two terms, I get that my alpha and gamma should be 1 by square root 2, and my beta and delta should be 1 by square root 2, which means their product should be half, right? So I'm actually having alpha, like I'm having contradiction here because it can't be both simultaneously 0 and 1. They are complex numbers, not magic numbers. Maybe there's a thing called magic numbers, I don't know. Okay, yeah, you see? So the state we have now is an entangled state. Okay, it's not like mathematically it is not so much fun to look at what entangled state looks like. But when you do computation, it lets us do teleportation, which is going to be fun. Cool. So now, like I said, okay. So the first, the unitary evolutions that we described earlier, like these X gates, identity gates, or H gates, they were single qubit unitary operation, meaning you kind of did something to just one qubit. But maybe you want to do something to both the qubits, right? Then you need to define a space of unitary operations which are like 4 cross 4 dimensional operations. Basically something that takes some 2 qubit quantum state and spits out another 2 qubit quantum states. And one such example that we'll use and will be relevant for us is the C0 gate. So the C0 gate acts on 2 qubit system, and the way it acts is it checks the first bit. If it is 0, it does nothing to the second bit. If the first bit is 1, then it flips the second bit. So if my C0 is acting on this state, so what it'll do, it sees the first bit is 0, so it won't do anything here. Here it'll see the first bit is 0, it won't do anything here. But here, it sees the first bit is 1, so it flips the second bit. So now if you see, this new state has my amplitude alpha 1 0 instead of alpha 1 1. And similarly, when this C0 is applied on this, it keeps this amplitude same, but it flips this value because the first bit is it's a 1 qubit, so it makes it as 0. Okay? So you see, this is an example of a 2 qubit unitary that works on taking information from both the qubits. It's kind of like it is taking information from the first qubit and then applying something for the second qubit. It's kind of creating an interaction or uncreating an interaction, whichever way you want to see. Cool? Okay. Yeah, now how do we construct an entangled state? Now look at this. So imagine you had 2 qubits, an initial 0 state, meaning you did not keep any amplitude on them. You can apply a Hadamard. And what does the Hadamard do? The Hadamard kind of gets this state. With the Hadamard, the first qubit becomes on uniform superposition of 2 bits, right? Like 2 qubits here, 2 bits, 2 bit configurations. And you still have this last state. Now when you apply C0, it takes the first qubit because it is reading the first qubit, it's 0. It keeps it as 0 0. But when it reads the second qubit, it reads it as 1. So it's going to flip the second part, which is 1, which is going to flip 1 0. So it will become 1 1. You see? And now, so now look at this. This was a tensor product state, right? Because this is a product state. I take this tensored with this. So this is a product state. But when I applied C0 on this product state, it became entangled. And now we saw that this is not a product state anymore. Cool? Any questions till now? No? Okay. Let's move on then. And okay, and you, if you're interested, you can try to see how to construct this other entangled state with a -1. Does anyone want to try now? It's not too difficult. Okay, let me tell you the answer. So in this circuit, if I had started with a 1 state here, then I would have had at this point 0, -1. Okay? And then I'll keep this thing same. I would have just got 0, 0, -1, 1. You see? Okay? Cool. Now similarly, how do we extract information from 2 qubits? We measure. We can do two things here. We can either measure both the qubits at the same time, or you can measure any one of the qubits. Okay? If you measure both the qubits at the same time, you will get, like say you'll get 0, 0 with this probability mod alpha 0, 0 square, so on. You get this state with this state with this state with this. Okay? And if you just measure first qubit and don't measure the second qubit, then you get 0 with this square plus this square, because you want to see what is the probability distribution if you get 0. And you will get 1 with the first qubit with this mod square plus this mod square. Similarly, you can make calculations for measuring the second qubit. Okay? Yeah, like I said, for the second qubit, you get 0 with this probability this square plus this square, and you get 1 with probability this square plus this square. Okay? Cool. Okay. Now, the first cool thing that quantum computing offers, or let's say doesn't offer. Okay. Now, classically I can copy information, right? I can have C0 gate, classical C0 gate, which can basically read any bit of information into a new register for me, okay? But quantumly, we cannot copy information. And this is one cool thing that quantum mechanics allows us to have nice QKD kind of key distribution protocols. Because you cannot copy quantum information, any eavesdropper who is on the channel cannot really copy information. So in some sense, your information can be a bit more secure. There's a lot more other probability arguments that go on, so that's why I'm saying mostly secure. Okay? Now let's look at the no-cloning theorem. So what this no-cloning theorem tells us, that if I have an arbitrary quantum state psi and a blank register 0, there is no unitary that I can use that will give me the first state psi and the second state also as psi. Imagine, like, what is copying information? Of course, if you knew the information, then you can just rewrite it. So that's not called copying. Copying is like you don't know what the information is, but you're able to copy it, right? So any unitary that can perform, can take psi and 0 and give me psi and psi, doesn't exist. And the proof is quite simple. So let's see the proof. Okay. Now again, maybe contradiction. No, maybe we don't even have to use contradiction here. Okay. So yeah, actually we do. Suppose that that unitary existed. Okay. Now if that unitary, 2-qubit unitary existed, that took a state psi and took a state blank state 0 and gave me psi and psi, then that unitary will also work on the 0, 0 and 1, 0 state also, right? Because it is a unitary that copies no matter what. So I apply that unitary on this state. I take this psi 0, I just apply it linearly. Now what I get here, you take out alpha, it's a scalar multiplication. You do u on 0, 0. U on 0, 0 is nothing but 0, 0, so that remains fine. You then do u on 1, 0. U on 1, 0 becomes 1, 1. So now your unitary, which is supposed to do psi psi, doesn't do psi psi, but does this instead. Now this state is not equal to this state. If I open psi and psi, like if I open the tensor product of psi and psi, this is alpha beta as vectors, you will actually get this state. But when you apply the unitary linearly, you get this state, which is not equal. So this kind of shows that there doesn't exist any unitary that can do copying on any arbitrary psi state. And instead, it can only copy if your state is 1 or 0. Yeah? Cool. Oh, yeah, it was one of these early Nature papers that was like just 1 page long, but it had like amazing impact because now cryptographers use QKD and things like that on it. Now, teleportation. Okay, cool. Okay. Any questions till now? No questions? Okay, what do you guys think teleportation is? Sorry?
From A to B.
Yeah, but what goes from A to B?
Spooky action at a distance.
Yes.
That's what we want in time, right?
Yeah, spooky. But teleportation uses entanglement as a tool, so. Okay. Let me strip out the fun of the word teleportation. So I'm going to describe teleportation mathematically now, but it is still, I think it is still a fun thing to see that nature offers us this. Okay, so now imagine we have Alice on one side, we have Bob. Now they have a classical channel between them, okay? I am stressing on the word classical here, the reason will be clear. Now they, apart from having this classical channel, they also share an entangled pair. So they share this state. This is an entangled state that we just constructed we kind of created in the circuit, right? Like we took some 2 states and we constructed the states. So this is possible to construct. Now imagine the first qubit Alice took with it, the second qubit Bob took with it after they constructed the entangled pair, okay? And now what Alice wants to share with Bob is a quantum state psi. Alice doesn't know, maybe Alice knows, maybe Alice doesn't know, but this quantum state psi is represented by alpha and beta, right? And like we discussed, how many possible psis can be there? Infinitely many. So, but I only have a classical channel. So if I have infinitely many possible states, but only have a classical channel, how do I send this information to Bob? That is what teleportation is going to help us achieve. You get the question right now? So we have the state psi. Maybe we know, maybe we don't know, doesn't matter. And we want to send this information because what is psi? Psi is just a vector, right? It is just information about alpha and beta, that's all. We want to send this information to Bob using a classical channel, okay? Yeah?
If we know it matters.
Then also the precision matters. Suppose we knew, okay? Suppose I knew this is some 1 and 0. Then I know I can send Bob, oh, I'll always send this because I can always tell Bob, I'll just send you the alpha square or something, and then you can send. But what if the alpha or beta was really long, like say value of pi or something, like 1 by pi or something like that? Then how do you send it? So then you can't send it fully, right? You will send it maybe to some approximation to some bits or something, some precision. But with teleportation, you can send it fully, like no approximation, nothing.
Yeah, that was the point I was trying to say. If you know the state,
Yeah.
you can.
I mean, if Bob knew the state, then the channel itself is redundant. You don't need the communication line. But say Bob didn't know, Alice knew. Still, Alice will need like if I want to send it in a discrete way, I will need bits to represent. Yeah. And then why did I stress on this classical channel? Because if I had a quantum channel that could send the qubit itself, then of course I can just send the psi using the optical fiber or something. But I only have classical channel, so I can only send bits. So that is where we're going to come. Okay? Cool.
What do you mean, like something like the amplitude numbers?
Yeah, like say 1 by square root 2.
Pi is still confused.
Okay, say, I see. Okay, what I mean is like say there is a number that I cannot compress. Like 1 by square root 2, still I can write it in certain way. But say there was some alpha value that I can't compress digitally. Then I want to send it. So yeah, that is what I meant. Like yeah, pi, maybe you can still have some encoding of the word pi and then say, yeah, I agree. Cool, good point. Shall we dig into the protocol then? Okay, let's see. So now, the circuit is very simple, but I will need to kind of show how the work happens. And we'll also need to, so I'll do it in the next slide. So this is the circuit for teleportation. Now the red dots are the qubits that are with Alice. The blue dot is the qubit which is with Bob, okay? At the beginning, Alice has psi, and Alice has first qubit of this entangled pair that is shared between Alice and Bob. And Bob has only, Bob has no information about psi in the beginning. It only has part of the state, right? It has the second qubit that is from the EPR pair. Yeah, this entangled state is called EPR state, okay? Now, by the end of the protocol, Bob will have psi. That's the claim, okay? Yeah, now let's see. So now what first Alice does is Alice performs a C0 gate. So first it just writes down, so I'll just open this state up, so I write it down. And I don't even perform anything, I just write the state down mathematically. So now remember, psi is just alpha times 0 plus beta times 1. This is just any psi, right? Like I'm writing an arbitrary psi. And now I open it up, so I just have alpha times 0, so I do a tensor product, so this 0 with 0, 0, 0 with 1, 1, I get this, 1 with 0, 0, and 1 with 1, 1, so I get this. Okay, I've not done anything. I just mathematically opened how the system looks like. Okay, then Alice applies a C0 on its 2 qubits. Now remember the setup. Alice and Bob are far away. They are separated by some classical channel. But Alice can perform C0 on its own 2 qubits, right? It has part of the EPR pair and it has psi that is there with Alice. So Alice performs C0 on both of these qubits. And then the resultant state becomes, so the first one is 0, so nothing happens, 0, nothing happens. For this state, it becomes 1, 1, and this state becomes 1, 0. Yeah, nothing, just C0 it applied. Now Alice performs a Hadamard gate on its first qubit, which is again an allowed operation, right? Hadamard is a gate, Alice has the qubit, why not? Then puts it. Then it gets, now the final state, I just rewrote these terms. It's not, if you just apply Hadamard to this state, you will get this state, but I don't want to calculate it here, so just trust me on this, and I just rewrote it in this way, okay? Now, this is the state that Alice and Bob together have at this point, okay? So all gates are applied, but now measurement is left, okay? So at this point, this is the state. Now look at the state once. So if I just read the state, like I want to understand what the state means. This state means if Alice were to measure the first 2 qubits, and if it were to come 0, 0, then the state at Bob's end would have been alpha 0 plus beta 1. If Alice measured the state and the state first 2 qubits, because first 2 qubits are with Alice, so it can measure. If the measurement outcome was this, then the state that Bob would have is this, alpha times 1 plus beta times 0. Similarly, if Alice were to measure and get this as the outcome, Bob would have this. And if Alice were to get this as the outcome, then Bob has this. This is just the mathematical, okay, I mean, the state is the same, but I'm interpreting it mathematically. So now when Alice measures and gets one of these outcomes, all it has to communicate to Bob is which of these outcomes Alice got. Because if Alice got this, it has to just tell Bob, hey, I got 0, 0. Then Bob also knows what the protocol is, right? So then Bob knows that it has got state psi as it is. But if Alice measured this first 2 qubits and got this, then Bob knows that it doesn't have the state psi, but it has the state psi x on the psi gate. You see, what is the state? This is nothing but x on the state psi. Remember, x was just flipping the values. These are not the same states, right? You see? Yeah? And if Alice were to measure and get this outcome, then Bob knows that, oh, what he has got is z times psi. And if Alice were to measure and get this outcome, then Bob knows that the state that he has got is x times z times psi. So it kind of understands that, oh, depending on what Alice gets, it knows how to go back from whatever state it has to psi. You see what is kind of happening? And for communicating whether it is this outcome or this outcome or this outcome or this outcome, how many bits does Alice need? Just 2 bits, right? Because it only has to tell Bob, hey Bob, I got either 0, 0 or 0, 1 or 1, 0 or 1, 1. Basically, it basically communicates the bits by Z and this tiny z and tiny x. And whatever its outcome is, Bob just applies that and gets the state psi. Isn't this cool?
Alpha can even be some uncomputable number.
Yes, exactly. That's like, this is one of my favorite protocols for the same reason. Like, because alpha can be like of arbitrarily long precision. No matter what my alpha betas are, this protocol works exactly under the assumption that the EPR pair, everything is stable, okay? Like, and another cool part is, I think maybe decades ago, in Netherlands, the teleportation protocol was also practically implemented. And I think they teleported maybe around 90 or 100 kilometers. I might be wrong on the numbers, but they did. But because like for us, a lot of technical challenges come, right? You cannot maintain the quantum states for a long time. You don't know whether the unitaries that you apply actually correctly because they apply with a lot of error. So there's a lot of challenges that happen. And in spite of that, scientists were able to do this teleportation protocol. Cool? Any questions? Yeah. So now, do you think we can teleport a cat? Theoretically, yes, yes. Just write the cat as some state psi, and then you're done. Okay? Yeah, cool. But okay, so till now what I've been discussing is like one thing that I discussed is something that seems impossible to do classically, that is teleportation, that we can do because of quantum mechanics. And the other thing that we saw was something that we can't do in quantum mechanics but can do classically, that was the no cloning thing, right? We can clone information classically, but we can't do it quantumly. Now, both these quantum phenomena are used in cryptography for symmetric key exchanges and QKD, these kind of protocols. In fact, if I'm not wrong, I think there's a lot of research happening in implementing QKD in Netherlands, in Eindhoven, in fact. But I don't know which all universities are part of that. But now, PQC, like post-quantum cryptographers, they don't care about these kind of quantum phenomena, right? We care about computational advantage. And what do I mean by computational advantage? Like, we want fast algorithms. We don't want no cloning or teleportation, but we want to compute something much faster than what classically computers can do. So now we will look at some examples of quantum speedups, okay? Looks like I'm not going to be short in this talk. Okay. Yeah, okay. So before I talk about quantum computation advantage, I have to kind of explain how we interact with the input on a quantum computer, okay? Now, say I want to compute this function, okay? I know this function. I don't know the input, but I want to compute whether the function on some input computes to 0 or 1, okay? And I can ask, so my input is unknown, but my function is known. So I can ask my classical computer, what are my bits? Say, like I want to ask, what is my 7th bit of x? Because this is an n-bit function, right? N-bit input, like this x1, x0, x1, x2, x3, and so on. What I want to analyze is the number of queries I need to make to this input in order to compute my function. Okay? So let's look at the example. Suppose I want to compute OR. Does anyone know OR? Everyone knows OR function? So OR function basically computes to 1 if there is at least one index I such that xi is 1. Okay? Or on all, if all the values here are 0, then OR on that is 0. Or just ask, does there exist an index I such that xi is 1? That's all, okay? So now how do I compute classically? I'll ask, hey, what is x2? Say 0. Then I'm not done with computation, right? I can't conclude. x3, it's also 0, not done. x5, 0, not done. Oh, xx is 1. Now I know there is an index which has 1, so I can output the value as 1, okay? Now what do you think will happen? How many queries will I need to make to such a input if I was doing classically, so that I perfectly determine whether I am in a 1 input case or a 0 input case? Yeah, like I'll need omega n queries, because I might have to actually, in the worst case, query all the indices, because imagine my algorithm was querying sequentially, like it was first asking x1, then x2, x3, and it's possible I'm in the input where the last one, till the last one, I don't know whether I'm in a 0 input or 1 input, right? So potentially I need n queries. Now, quantumly, if I want to ask the same question, I don't have this kind of a model, because now I can ask this question in superposition. Meaning, instead of asking what is the value of x1 or x2 or x3, I can ask this question, hey, what are the values of x1, x2, x3, xn, all in superposition, okay? I can ask that. But I can't really do much by just asking that, because the only way I can interact with my quantum system is by measurement. And you saw, right, in measurement, the things are probabilistic. I won't always get the right answer. But what I can do is I can then apply some unitaries. Every time I ask this question, I can apply some unitaries around it, so that by the end of my computation, I have a lot more chances to get the right answer. Okay? This is a general thing. I will see some algorithm, and then you'll be convinced why this general thing works. But okay, so our model is, we start with an all 0 state. So we do, like, no matter what my x is, the input is, I don't know, but I start with the all 0 state. I apply some unitaries. I ask the question, what is x7 or what is x10? I am also allowed to ask that in superposition. So I ask those questions here. Again, apply some unitaries. Again, ask some questions like that. And I do that. In the end, I measure my state. Okay? Now, this is a tiny technical detail, but is not very relevant for this talk. Yeah, maybe we can skip it now. Yeah. Okay. So yeah, but how do we ask this question? Like, how does the unitary operation looks like? So if I ask what is my index I, so this is the index that you ask. This is the register where your xi gets stored, and this is just some work register, okay? So this is a unitary operation, and this you are allowed to ask in superposition. So this is how my OX is going to look like, okay? And another way of interpreting the same operation, so this is called the bit query, because you kind of, whatever answer you got, it gets XORed with the register here. You can also get it as phase information. This is like, basically here you get it copied onto this B dash, but here you get it as a phase. It is just another way of accessing the same information. And you can construct this oracle using this oracle, and this is the circuit for it. So if I have only access to this way of accessing the input, I can construct this way by just doing this, okay? Yeah. But for now, just believe me that I give an index I, and I give some register Z. I ask the question, and I get this information about xi as a -1, as a power to this -1 phase. So if xi is 0, this will be just 1. If xi is 1, this will be -1. You see, it is distinguishing, right? In one case, it gives me just z. In the other case, it gives me -z, okay? Now let's see how we can use this towards our computation. Now the first example that I will show is this Deutsch-Josa problem. Here, here we have this function. It is a particular function. We don't know the input, again, like I said, but we want to know whether we are in a 1 input or the 0 input case, and how is the function defined. Additionally, we are also promised that, first of all, how many possible inputs are there to this function in general? Did I hear 2 to the power n? Yeah, exactly. So in principle, I can have 2 to the power n many x that I want to evaluate on, right? But now I'm additionally promised that I don't need to have all the inputs. I only need to understand what the function behaves on these kind of inputs. So either my x will be an all 0 string, means it will have 0, 0, 0, 0, 0, 0, n of them, or it is an all 1 string, which means 1, 1, 1, 1, 1 till n, or it has strings of exactly n by 2 ones and n by 2 zeros. Yeah, assume n is to be even. Yeah, actually, yeah. Okay, so you understand? I just want to compute whether I'm on this case. This is called the constant case and this is called the balanced case. I want to understand whether my input is a constant input or a balanced input. That's the question I'm asking. Now, what do you think we can do? Of course, we can check all the n indices, right? We can ask, I can be a very stupid algorithm. I can ask all my n indices what my values are, and then I can determine whether it is this or this. And the worst part is, classically, if you want to compute this function deterministically, meaning without any error, you do need n by 2 plus 1 queries. Can you say why? Why do I need n by 2 plus 1 queries? Because I have the promise, right? Either I'm in the balanced case or I'm in this case. So if I just, like if I get n by 2 plus 1 queries and if I get all zeros, then I know that I can't be in this case, then I can be here, or same thing with 1. Yeah? Okay. But classically, that's the best we can do. But quantumly, we can get tremendous speed up. Any guesses in how many queries we can do this quantumly? Sorry? I can't hear. Okay, we'll see the number. It'll be a very surprising number because you can now fill in the biggest number you want to fill in for n, and quantumly it is still going to be surprising. Okay, cool. But let's first do the n equals to 2 case, just to get a feel of it, okay? So in the 2 case, what happens? All I want to decide is whether it is constant. This is a constant case, right? But if my 2 bits are same, it's a constant case, or it is a balanced case, right? Because n is 2. There are only 4 things we can expect. Classically, we have to use at least 2 queries, but quantumly, we can do this with 1 query. And let's see how we do it, okay? So again, recall, yeah, I have time, yeah. Now recall that we can take this index, how can we access the input quantumly? We can take index I, we can put it as a phase, right? We can put it as a phase -1 to the power of xi times this I, okay? So now what I'm going to do, I'm going to start with a single qubit state, which is a 0 state. See, that is not input independent. I mean, it is not knowing anything about the input. It's fine, it's allowed. Now, I put this qubit in uniform superposition. How do I do that? I just apply my Hadamard gate on this 0, and what do I get? Uniform superposition of 0 and 1. All good till now? Okay. Now, I ask the query in superposition. Remember, I said I can give in an index and I can get the xi information as a phase, okay? So I gave, this acts as my index. Now I ask this query in superposition. So I ask them, what is x0 for this part? I ask for this part, what is x1? And I get it as a phase here. You see? And for just clarification, I am indexing starting from 0, just for simplicity, okay? Like my first index is x0 and the last one is xn minus 1. Now what do you think I can do? Now what are the possibilities here? Either I'm in the constant case or balanced case, right? So if I was in the constant case, then x0 and x1 should be same. And if both are same, then I will have 1 by square root 2 and 1 by square root 2 and a global possibly minus sign, but maybe not also, depending on what x0 and x1 are, right? And if they are different, what will happen? The first one will be a -1 or +1, and the second one will be opposite. So I will have 0 minus 1 state. So either I have 0 plus 1 state in the first case, in the constant case. In the second case, I have 0 minus 1 state. So basically, if I applied Hadamard to this again and just measured it in computational basis, I would get which state I was in. So what classically I did it in 2 queries, I could use just one superposition query, but queried in superposition, and one query, one oracle access, and I got the output. You see? Now, let's do it for the general case. So what can we do for the general case? Because, I mean, constant is not fun. So classically, we can do that much. Quantumly, we can get tremendous speedups. But before I show the general case, I need little bit more of background. So yeah, now look at this. If I apply Hadamard to the first qubit, I get 0 plus 1, and there's a square root 2 hanging. Here also I get that. And when I multiply them together, I get this state. You see? This only like mathematics, like this just linear algebra. You take it as 2 vectors and you multiply this big unitary, you'll get the same thing, okay? Now, if I have n qubits, meaning like I have 0, 0, 0, 0, n of them, and I applied Hadamard on all of them, then what I end up getting is actually this state. I get superposition of all possible indices in 2 to the n, little n. That many indices I'll get with this normalization factor. Basically, uniform superposition of all my indices in 2 to the little n, because I'm using n qubits. Is that clear? Yeah? Okay. Now, why is that important? We'll see soon. Now, okay, one more thing. If I had one of the state as 0 and the other one as 1, I will get some minus 1s involved, okay? Because this is also just linear algebra. You open it, you'll see, okay? And in general, what happens is, if I had, say, I1 up to In, meaning I1 is either 0 or 1, but it can be anything, then I get this complicated looking state. Just trust me on this, don't have, like, you can work it out later. But basically this minus 1 kind of works as this, it's whether or not it is minus 1 or plus 1, it will depend on what is the inner product between I and j, okay? This is also just linear algebra. You open it up, you'll get it. And this is what is going to be relevant for us, so we will see why. Okay, so just remember this part. Try to work it out at home, okay? Yeah. So now, for the Deutsch-Jozsa problem, remember, we want to solve the general case now. We don't want to solve the n equals to 2 case. We want to solve n equals to n case. So what do? Whatever this little, so remember your capital N was 2 to the little n, right? So I'll just take little n number of qubits. I apply Hadamard on each of them. And then I do a oracle, like this is like querying the input. Then I do Hadamard again, and then I measure. So in this circuit, how many times have I queried the input? So in this circuit, actually I have queried the input just once, because I'm using OX only once. But what is going to happen is, no matter what your n is, I will in the end get the actual answer like deterministically, and we'll see this. So let's calculate. So what is the state here? Remember I said you apply Hadamard on each of these qubits. This state you can write it as uniform superposition of all your, so this I you can think of as qubit, like binary representation of this I. So any value in 2 to the little n, how many bits do you need to represent it in binary? Log of 2 to the n, right? That is n. So basically in n bits you can represent this I. This is what this quantum state is storing right now. Now you applied this, you basically now applied this query oracle. You asked, what is my xi? But you asked in superposition. So it gave the answer also in superposition. Okay, so it gave you this answer, minus 1 whole power xi in superposition. Now someone might say, oh, why don't I just measure it now? But that is not going to help, because the amplitude is still, like the amplitude square is still 1 by 2 to the n. So if you measure, your state will just collapse and you'll get some random index, that's all. So that is not going to help. But now what I do is I apply Hadamard, and after applying Hadamard, my state actually now looks like this. And this you just take it as black box now, but if you want you can calculate at home. Okay? Now let's analyze. The cool part is, let's look at the amplitude of just 0 to the little n state, meaning if my j was just all 0 string. We are just analyzing like how much the amplitude is. Now, j is an all 0 string. So, in a product with I, no matter what your I is, if you do it with an all 0 string, what do you get? 0, right? So, this part becomes just 1. So, it's not interesting. And what is left is this value. Okay? So, this is the amplitude on your all 0 string. Now, remember what the promise was? The promise was that either we are in a constant case, right? Or we were in a balanced case. So, in the constant case, all your xi will be equal. Either they will be all 1 or they will be all 0. So, if it is the constant case, this summation term will get 1 or like minus 1, right? Because if it was, say, xi was all 0, what does this become? 1. How many such terms do we have? 2 to the n? 2 to the n divided by 2 to the n, 1. This is the thing, first one. If it was all 1, if xi was all 1, then this whole thing will become minus 1. How many such minus 1s I have? 1 by 2 to the n. So, that would become minus 1. But if this was balanced, then I know there will be half of the indices which will be minus 1, half of the indices will be contributing to xi to be 0, which means this will contribute to 1, and they will cancel out, and then you will get the amplitude as 0. So, if I just measured all these states in the end, and if I get 0 state, then I cannot be that I am in the balanced case. You see? Because the amplitude on that is 0 when it's in the balanced case. So, if I get this state, I cannot be in the balanced case. But if that means I am in the 1 case. So, this is how I can distinguish. You see? And now, no matter what my little n was, no matter what my capital N was, all I did was one single query, but I was allowed to do it in superposition, and I got this computational speed up. So, what classically requires n queries, quantumly, I was able to achieve exactly one query. Now, this is something, right? Now, this is kind of the thing that Shor uses, or Shor observed and sped up factoring. And we will see the overview. We will not get into the full algorithm because that's rather complicated, but complicated for this context. But you can check it out on your own later. Okay? Cool. Yeah. So now what Shor's algorithm? Oh, wait. Any questions before that? Before I get into Shor's? But do you guys believe me? Yeah? Okay. Cool. Okay, then let's get into Shor. It'll be really bad if I still finish fast, but I have 2 algorithms. I hopefully will take the 30 minutes. Let's see. Okay. So what is the Shor's algorithm? Like, what are we trying to do with Shor's algorithm? We want to factor a very big number, okay? So now the thing first he noticed was that factoring can be reduced to period finding. So suppose I want to factor this number n. What I could do is, I'm going to reduce this to period finding. Now, I'm promised that n has a factor. Now, suppose that there is this some random number r which is less than n. When I raise it to some power x, I get this. Okay, I'm just doing modular arithmetic. Then it would mean that this r power x minus 1 will be 0 mod n, right? This is just some little group theory. Now, if x is even, then I just rewrite this as 2 factors. This is just, a square minus b square, so I kind of broke it up as a plus b and a minus b, and which means this quantity here will be equal to some k times n, right? Because this equals to 0 mod n, that means it's some factor of n. Yeah? This is okay? Cool. So now if I could find this x for some r, then I'm done, right? I kind of got some non-trivial factors for n, because they can't be dividing n like k times n or something, okay? So yeah, in fact, this with high probability, I mean with probability greater than half, you will find some, like if you just randomize this process, you randomly pick this r, with probability half, you will find that this satisfies this. So now all it remains for us to factor n, we just need to find this r and this x. And this x here is called the period, and we want to find this period for r such that it satisfies this condition, okay? So this was the first observation. Now I'm not sure if Shore made that observation or the observation was already made, like this reduction from factoring to period finding, but we'll just follow that once we have this reduction. Now what quantum part does is basically speeds up this period finding thing. So classically, whatever algorithm we know runs in 2 to the power log n times log n to the power alpha, and see, we want to factor this n number, right? So the input size for us is log n because we are given the number as bits, which is log n. So this is an exponential time algorithm. But Shore's algorithm will only run in polynomial time in the number of bits that it is required to express n. We'll see the algorithm a bit. Okay. Yeah. So the algorithm for factoring. And like I said, I'm going to describe just the period finding thing. I'm not going to say how it will combine all the answers it gets to the solution of n. So, okay. Now, first thing that we do is we compute a superposition of all possible periods that can be possible, right? That's not many, because if we have n as a number, you can't have too many periods. So you just construct superposition of all these values here, indices here, and the second state is just 0. Then what you do, you compute this f of x in superposition. So basically you have this x, and this f of x is nothing but what you had here. Yeah, your f of x is basically taking some random r, you're doing r power x mod n. That is the function. Your f of x is taking this number r, it's raising to the power x, and it's doing a modular calculation mod n. Okay? Yeah. So that you do, and that is efficient because you can do repeated squaring method, and you can do that for any x, not too expensive. Now you measure the last register. Now when you measure the last register, because you know there is a period, you know that this value keeps repeating, right? So you know your first register will only be there, like will only exist for s, s plus p, s plus 2p, and so on. And this is the p that you want to find. This is your, this is the x that was there on the previous slide, okay? And now one can do quantum Fourier transform on this state and get the value of p. And once you have the value of p, you can get the factor, okay? So this is the basic idea of Shore's factoring algorithm. And this quantum Fourier transform that you do on this p is the one is very efficient, and we don't have this procedure efficient in the classical setting. This is where the speed up comes from. And what it is kind of relying on, if you can see that this f of x is queried in superposition, right? You ask the quantum state to give f of x in superposition of all possible x's, and that is what it exploits. And that superposition we don't have in the classical setting. While Shore's algorithm breaks factoring and discrete log problems, it is not an algorithm that works for any of these PQC, like lattices or code-based cryptography problem. In fact, that is why these PQC candidates were even explored, because as of now, we don't see this periodicity of this kind hidden in these problems, but people are still exploring. Like, what if there is some periodicity that you can exploit to get this sort of speed ups in the quantum setting? But there is another algorithm, that is Grover's algorithm. Bart even mentioned that in his lecture today. What Grover's algorithm does is it quadratically speeds up the search procedure. So what Grover's algorithm does is, like, suppose I have this input x0 up to xn minus 1, and I want to find whether an index xi is equal to 1 or not. Like remember this OR problem that we wanted to solve classically. That is exactly what Grover's algorithm is also going to solve. But now classically, we feel, I mean, I did not give you a proof, but actually it will require omega n queries. Like I haven't discussed the proof, but just believe me. But quantumly, you can use Grover's algorithm and you can do it in square root n many queries. And even though this is like a square root speed up, but what Grover's gives us is like this kind of problem that it solves is a very general problem. It's like if you have a lot of items and you want to find like items that satisfy some conditions, then apply Grover's. So you will see when when we will be discussing some cryptanalysis talks in future, you'll see that many of these algorithms that exist, they will be exploiting some search space, and then they will be looking for some candidates that satisfy certain constraints. And in these kind of cryptanalysis attacks, you can use Grover's very easily because Grover is like, you can use it as a black box. You can be like, oh, I will just use Grover and search the space, so I will get a quadratic speed up. And theoretically, what that quadratic speed up will imply is that you have to make your security parameter double, right? But like Bart mentioned, because we don't have really good functioning quantum computers now, we are not in a bad state, but you never know what about in future. So, okay. So let's look at the Grover's algorithm. It's little more, okay, I find Shor's little more quantum-y. Grover's is more, what to say, linear algebra types. So let's see. Yeah, let's look at the algorithm. But before we look at the algorithm, let me remind you one thing. You see, when we describe these qubits and unitary operations and all that, what did we see? We saw that the qubit, any qubits or n qubit system, we can just represent it as a vector, right? Like some vector which is in 2 to the little n dimensions, and any unitary we can kind of see evolutions of these vectors. Basically, any unitary operation takes this vector and makes it into a new vector of the same dimension, but the values changed. That's all that was happening, right? So now what Grover's algorithm does is, again, as many quantum algorithms, it starts with an all-zero state, and it puts, it creates a uniform superposition of all the indices, possible indices. And that, how can we do it? How can I construct a uniform superposition of all the indices? Exactly. The Hadamard on each qubit will give me, if I start with the 0 state, the Hadamard with each qubit will give me this state. Yeah, perfect. So now what I do, now remember, what do I want to compute? I want to compute whether my input x has any index I such that xi is 1, right? That is what I want to compute. So I want to write, like this is just linear algebra now. I want to define a state, I call it as a good state, which contains all the set of indices that have xi equals to 1. I don't know this good state. I don't know this state yet. I'm going to find this state. But let me first mathematically write it. And suppose that the input that I have has t many indices which are 1. Then my good state will look like, if I construct uniform superposition of all these good indices, I will get this, right? It is just normalizing the amplitude here. And what will the bad state look like? And the bad state will be the rest of the state, which is all the indices that don't have 1. And because I said I have t many good indices, I should have n minus t many bad indices, and this is what I call the bad state, okay? Now, what Grover is going to help us is, it's going to help us find this good state with high probability. Okay. Now, any state I can write, like say this state, this is my starting state, this is just linear algebra, and I can write this any state as just some sine theta times good state, some cos theta times bad state, right? Look, this is also forming a basis. If you just multiply this with this, you'll get 0. Yeah, it's forming a basis. And I can just write any state as some sine theta this, cos theta this, and sine square plus cos square theta is 1. I will fill in the sine theta cos theta part. So in some sense, you can imagine this is your good state, this is your bad state, they are orthogonal, and you are, this u is this state that you started with, and you want to find the good state. Now, what Grover's algorithm does is it gives us a method for reflecting this u. This is the initial state that you started with. It helps you reflect this u about B and then about u itself. So it keeps doing this reflection. And if you reflect once, say I reflect and say this u and B, because it was sine theta, this was theta, right? The angle between this G and B, u and B is theta. If I reflect u once about B, I will get the new u somewhere down with theta, right? This is the new u I'll get. Now, if I reflect this state about u, I will get somewhere this place, which is this. So now, one Grover iteration is two reflections. First, it reflects about the bad state, then it reflects about the u state. So one Grover iteration helps me move my u state by 2 theta. And I keep doing this. If I do it k many times, I kind of get that my new state, because I'm reflecting, I kind of, if I do k many times, my new angle becomes 2k plus 1 theta, and this remains same. Yeah? So my new theta dash is this much. Now, when will I get a good state? If I suppose, just for fun's sake, suppose this sine square 2k plus 1 theta was equal to 1, then I will never get a bad state, right? If I measure this, and if this was equal to 1, I will never get a bad state, which means I want my 2k plus 1 theta to be equal to pi by 2. And then if I just do k equal to this much, I get that value. You see? So this is, okay, this is with high probability because you can't always get exact, right? Like this has to, if you want deterministic no error, then this has to be exactly equal to 1, which is not possible because you don't know k, you don't know n. But there are methods to guess it, and then if you run it order square root number of times, n number of times, this Grover iteration, you will get this good state with high probability. And this is what Grover's algorithm is. Any questions? Okay, I have still not finished my time, but I finished my talk. So thank you. Yeah.